Welcome back. In this video, we're going to continue exploring thermochemistry by focusing on calorimetry. And we'll use calorimetric data in order to determine the heat of a reaction. So what is calorimetry? Calorimetry is the experimental measure of heat flow. And we've actually used calorimetry before. Remember back in chapter 13, we looked at phase changes and we described the temperature change of a substance as we added heat to it. We said if you take that substance as a solid, initially as you add heat, the temperature is going to go up. At a certain point, the substance will start to melt. Once it's completely melted, we can increase the temperature again by adding more heat. We can then vaporize the substance and then eventually increase the temperature again as we add more and more heat in the gas phase. And so this, we are able to compute the energy involved anytime that there was a change in temperature. When we had a phase change, we used this relationship where we related the heat to the enthalpy of the phase change. Similarly, we can use this mathematical relationship to describe heat changes for chemical reactions. The way that we do this is similar to what we've done already. This Q is describing the Q of the surroundings. And so it uses the specific heat of the surroundings and the mass of the surroundings and the temperature change of the surroundings. So what is our surroundings and what is our system? Typically, the chemicals and the chemical reaction is going to be our system. Therefore, everything else is the surroundings. That will typically include water, and it's definitely going to include the thermometer. So when we have a reaction that says the solution increased by 10 degrees Celsius, then what's really the proper way to interpret that is that the thermometer measured an increase of 10 degrees. Therefore, the thermometer's energy went up, and it gained that energy from the reaction. So that was an exothermic reaction. We can measure temperature changes for these chemical reactions using what's called a coffee cup calorimeter. This measures the temperature through a thermometer when we add together different solutions, and it does it under constant pressure, and therefore the heat that's given off is equal to the enthalpy. So let's walk through an example. When a student mixes 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1.0 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resulting solution increases from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the enthalpy of reaction in kilojoules per mole of hydrogen chloride. Assuming that the calorimeter loses only a negligible quantity of heat, the total volume of the solution is 100 milliliters, density is 1 gram per milliliter, and the specific heat of the solution is 4.18 joules per gram degree Kelvin. Let's first evaluate which statement is true. A, the reaction was exothermic. B, the reaction absorbed heat from the water. C, the products of the reaction are higher in energy than the reactants. Take a moment to think about this on your own. Welcome back. So, what do we know here? Well, we know that our system is going to be expressed by the chemical reaction. Sodium chloride reacting with hydrogen chloride, sodium hydroxide with hydrochloric acid to produce water and sodium chloride. That's our system. Our surroundings includes all of the other water that's in the coffee cup calorimeter, the calorimeter itself, the thermometer, etc. And our thermometer measured a temperature increase of about 6.5 degrees centigrade. Since the thermometer registered an increase of its temperature, that means the system must have given off that heat. Therefore, the reaction was exothermic. Instead of heat being absorbed from the water in our coffee cup is what's absorbing the heat. And since the reaction was exothermic, that means if we were to take a look at the energy of our reactants, then we must have gone down in energy and given off energy to our surroundings. Therefore, our products are lower in energy. All right, let's talk about a general approach for solving this kind of a problem. As we've talked about already, dealing with stoichiometry, you want to ask yourselves, what am I trying to find here? And we're trying to identify the heat of the reaction which is measured in kilojoules per mole of hydrogen chloride. We're given a variety of information here that could be useful. And we're going to need to know we need to know in total how much energy is released. We need to find how many moles of hydrogen chloride, hydrochloric acid, were used. This is ultimately what we need in order to solve our question. So what we'll want to do is to write out a balanced chemical equation and identify the amount of reactants involved in the system. Drawing pictures here can be useful as well. We want to calculate the heat that's transferred into or out of the system, and then use the heat of the system to identify the heat of reaction per mole of either the reactants or the products, depending on what the question's asking for. In this case, we're wanting to find the heat of reaction in kilojoules per mole of hydrogen chloride. So we need to find the heat of the reaction and the moles of hydrogen chloride. Our reaction is 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide to produce 1 sodium chloride and 1 water molecule. We can then organize the information that we're given in the table in order to help us to solve this. So we know that we've got 50 milliliters each of hydrochloric acid and sodium hydroxide. We know that we need to find the limiting reactant, and so in order to do that, you need to know the number of moles. When we have solutions, we can find the number of moles by using the molarity. Therefore, the moles of each reactant can be found by taking the volume and multiplying by the molarity. So that's 0.05 moles of hydrochloric acid and 0.05 moles of sodium hydroxide. To find the limiting reagent, what we can do is evaluate the ratio, how much hydrochloric acid, if we were to use all of our hydrochloric acid, how much sodium hydroxide would be needed? And the answer would be 0.05 moles. Since we have 0.05 moles, that means that we have the perfect amount of each reactant, and therefore they're both the limiting reactant. So we know that we have 0.05 moles of hydrochloric acid to use. Now we need to find the heat of the reaction. To find that, we first must find the heat of the surroundings. We can do that by multiplying the specific heat times the mass of the surroundings times the change in temperature of the surroundings. The specific heat was given as 4.18 joules per gram degree Kelvin. Our mass we can find by taking the volume and multiplying by the density. That's 100 grams. The change in temperature of our surroundings is taken from the final minus the initial temperatures, or 6.5 degrees Celsius. And it's important to remember, as we've talked about already, that the change in temperature in Celsius is the same as the change in temperature in Kelvin. Therefore, our heat of our surroundings is taken by multiplying the specific heat times the mass of the surroundings times the change in temperature of the surroundings. That's equal to 2,717 joules. To find the heat of the system, or the heat of the reaction, we need to take and reverse the sign, because all of the heat that was absorbed by the surroundings was given off by the system. So that's a negative 2,717 joules. To find the heat of the reaction, we need to take our heat and divide by the number of moles of that reactant. So that's 54,340 joules per mole released, or negative 54 kilojoules per mole. Now, does this answer make sense? Well, we know that the reaction was exothermic. We know that because the temperature of the surroundings went up. Therefore, we would expect to see an enthalpy of reaction that's negative. Thanks for watching this video. Have a wonderful day.